Okay, ladies and gentlemen, this talk is about quantum numbers, which are going to tie in with electron configurations, which are going to tie in with those rules that we talked about um, for filling orbitals within electron configurations, things like Hund's rule and Pauli exclusion principle and such. So let's get going here. We have quantum numbers that we're going to talk about, and quantum numbers are ways to describe these orbitals that we have, these locations for electrons. And so we'll start with the very first one. We've kind of alluded to this in our last video, and this is our principal quantum number. And this is going to be designated as n, lowercase n. The smaller n is, the closer the electron is to the nucleus. The further from the nucleus, the larger your n is. So essentially, n is pretty easy to take a look at. Let's say we're taking an example of hydrogen, and hydrogen has one electron to deal with. And so we would say hydrogen is 1s1, and so this 1 is telling us that n equals 1 for hydrogen. If we were looking at lithium in the second period on the periodic table, lithium atomic number 3, we would do an electron configuration of 1s2, 2s1, and that would give us a total of 3 electrons, and our highest energy level there is 2, so we would say that n equals 2 for the electron that is in the 2s orbital. And so that's how we deal with principal quantum numbers. Pretty straightforward. The next one we call azimuthal quantum number, or sometimes called the angular momentum quantum number. They're kind of used interchangeably. And this has a designation of lowercase l. Lowercase l. And this one describes orbitals. So it's essentially if L is equal to an s orbital, those spherical orbitals, we say that the value of L is going to be 0. In the p orbitals, if you have a p orbital, L will describe the p orbitals as having a value of 1. In the d orbitals, and you can see it's just increasing, it's going to be 2, just increasing by 1. And in the f orbitals, L is equal to 3. So here, to give you an example, let's say if we're looking at helium with atomic number of 2, we can do our electron configuration of helium, which is going to be 1s2. That makes up for our 2 electrons there. We would say that this guy has n equals 1, and because it has an s orbital, we would say L is equal to 0, because anytime you have an s orbital that's being described, it's going to be 0. And so that's how we do that for the azimuthal quantum number. We can give you another example here. Let's say we're looking at magnesium. Actually, let's not look at magnesium. Let's do something a little bit different. Let's do let's say titanium. Titanium is atomic number 22. And if we were going to do noble gas electron configuration for titanium, we would do argon, and then we would go into our 4s2 and 3d2, just like that. So if we were describing an electron in this energy level, the highest energy level, it would be a d. And so we would say that L is equal to 2 for that electron. And you'll see how this all plays out here real quickly. Magnetic quantum number is, we call it, has the symbol designation of m sub l, and this is the orientation of our orbital. Now, this is what m sub l is defined as. M sub l has values for m sub l are going to be a range. And the range is from negative L to positive L. So m sub L is dependent upon what L is. And so essentially, if L is describing an s orbital, as we talked about before, the value is 0. And so then m sub L has to be also 0, because there's that's the range of negative L to positive L. But it changes if L is equal to 1, which would describe a p orbital, as we talked about before. So then m sub L is going to be the range of negative 1, including 0, to positive 1. If L is equal to 2, m sub L is equal to -2, -1, 0, +1, and +2. That's the range of 2, and obviously if L, oops, I'm sorry, that should be F, but that's thinking it, I'm thinking the orbital rather than the number. It's actually 3, so we can see that m sub L is equal to -3, -2, -1, 0, 1, 2, and 3, and there's our range of 3. Now, hopefully you can see, remember that L, let's go back up to this first one here, L equals 0, and remember this is describing an s orbital. Okay, no big deal. Here we're describing a p orbital, and remember p orbitals have 3 sublevels, right, to hold a total of 6 electrons, and that is what designates -1, 0, and +1. There's your 3 orbitals. Here, remember, we're talking about a d orbital, and so we have 1, 2, 3, 4, 5 orbitals, and F, 2, 3, 4, 5, 6, 7 for a total of 14. So these are describing, all the different orbitals within the s, p, d, and f is what we're getting at. The spin quantum number is the next one, which is called m sub s, and this is the spin of electron in an orbital either up, remember, or down when we do those complete electron configurations, the orbital diagrams. And these ones are really easy. M sub s is always going to be equal to either +1/2 or it's going to be equal to -1/2. So that's an easy one to figure out. It's always one of the other ones, depending on what electron it is. So let's give you an example of a problem and how it would roll out. So we'll say give possible quantum numbers. Give possible quantum numbers for an electron in a 2p orbital. Okay, so if you're in a 2p orbital, electron in a 2p orbital, first thing we're going to do is we're going to set up what n is equal to. And a 2p orbital is going to be quantum number 2 in the second period, so n is equal to 2 in that one. Then we're going to go on to L. Let me just put 2p right there just to remind us. Then we'll go on to L. Now, remember, in an L orbital, if you're an s, you're a 0. If you're a p, you're a 1. So L has to equal to 1 because, we had a 2p orbital, and p's are L equals 1. Then, m sub L. Remember, m sub L is going to be the range of what L was. So it's going to be either -1, 0, or +1 because L was 1 and the range is negative to positive L. And then m sub s is always going to be equal to +1/2 or -1/2. So there's a lot of possibilities we could say here. We could say n equals 2. We could say L equals 1. And those are the must-haves. And then m sub L, excuse me, because it is a range, this could be a -1. Or it could be 0. Or it could be +1. Doesn't matter. And then m sub s could equal 1/2, +1/2. So that's a possibility. Another possibility might be something like this. And there's a few other possibilities as -1/2. The only difference I did here is this is a +1 and this is a -1. We could also throw a 0 in there too, so they're both okay possibilities. And there's a few other ones that we could take a look at. Let's throw one out, another example out here for you. We'll say, is this a good description of an electron? So would these quantum numbers be okay in describing an electron? So let's say we have an electron and n equals 4, and that's definitely possible. 4th period, potassium, calcium, anybody like that. Maybe go over there, maybe bromine or argon, who knows? So that's okay. L equals 1. Okay, so if L equals 1, so now we know we're in the P block. Well, we definitely have a P block in our fourth period, so that's okay as well. Remember, M sub L is a range of positive to negative L. So is negative 2 okay? And the answer is no. That's not okay because this value can only be negative 1, 0, or positive 1 because it is dependent upon what L is. And it's not within this range and it's not okay. This last one, M sub S is positive 1/2. That's okay. We know it's either a positive 1/2 or a negative 1/2. Okay, and so that's kind of a primer on how you do quantum numbers. There's some more information in chapter 6 if you want to read about it tonight. And there's going to be some practice problems that are going to be up on the whiteboard for you to do. Make sure you have both sets of problems, the problems that we did in class today, plus these problems that are left for quantum numbers. These are both due by tomorrow. Have a great day.